So let's briefly recap some of the important things you should have seen in the video. One is this idea of having a layered software architecture. So this is a very common principle in computer science, that you try to break your system or application or whatever you're developing into so-called layers. And the main idea is that an application, if that is your application code here, should only call the underlying database system, but not the operating system or file system underneath, and also not the hardware underneath. Yeah. So in turn, the application, when the application will store data or read data, it will ask the database system, which in turn may ask the file system. And the file system, of course, is written on top of the hardware, like the storage devices and stuff like that. So that's a layered architecture. It's a simplified view on a layered architecture. Actually, there may be many more layers. And these layers may hopefully make life easier and not more complex. So that's one principle we have. And the other is, I will say that 5, 6, 7 times throughout this lecture, is this Lazyness Principle in computer science, but in particular also in data science and artificial intelligence. So the idea is, if you see an opportunity to map an existing problem to an existing solution, grab that opportunity. Do not reinvent the wheel. If you understand, hey, a similar problem has been solved before by someone else, hey, then the first thing you think about is, can I map that existing problem that was solved before and its solutions to my problem? Yeah? And by that you are probably able to exploit the existing solutions rather than starting from scratch. That's very, very important, and often leads to the second part here on the slide, that people miss an opportunity and invest insane amounts of time and work to reinvent something that was already done. And of course, for you and even for me, sometimes it's hard to understand what exists, which problems exist, which solutions exist. But over the years, you will learn more and more. You will understand, oh, there's a subfield in computer science that handles these kind of problems. So they have interesting solutions. That's interesting to know. You don't have to understand how those solutions work in detail. But once you are in a situation in a real project and see, oh, that smells familiar, that's probably in that subfield, you may be able to map it in that subfield rather than doing it from scratch. So typically doing it from scratch, something that was researched decades already by other people, doesn't make sense. You will never get the same quality. Okay, so we want to look at Google Maps today a little bit. What are the data management problems in Google Maps? And I also showed you on these slides, try to think along equivalence classes. So you can always group applications that do similar things into like a bucket, into a group. So, and we have this example here on the slide in the video. So in medicine, MRTM images, that's kind of a 2-dimensional or 3-dimensional data. It's similar to a Google Maps style service. Material sciences, any image data from any see-through device, be it whatever MRT style or X-ray devices that take pictures of some sort, be it in 2D or 3D. It's the same data management problem. It's just tailored to that specific application, but the data management problems will be the same. 3D star catalog. I think yesterday on Heise there was an article on that. I think that this is now 20 years old and was fostered by the database community originally. And now there's a catalog available where you can see, like, I think 200,000 galaxies are in that catalog, and you can explore them visually, but under the hood there's a database system, of course, and so forth and so forth. So those are basically all the same things. So with that, today we are on, we have that example, you looked at that hopefully. And today we will continue with operating systems. Well, database buffer was the last stuff in the video. And now we will look at these different storage layers and how the tasks they have and how they interact. If I show this one again, so what are the storage layers? It's a simplified image again of the storage hierarchy. You have these layers, layer 1, 2, 3, if you want to name them like that. Those are the caches, very fast, small memory that is part of your CPU, and there's main memory, and there's flash and hard disk. Each of those I'm calling a layer. Different layers that are stacked and have different properties. Again, the further away from the core, the slower. Yeah? So hard disk is relatively slow. Main memory is a bit faster. L3 is even faster, and so forth and so forth. And typically, the closer to the core, the smaller they are, because fast memory is expensive, and so forth and so forth. Yeah? So there are many trade-offs here to consider. And now we look a little bit at the different tasks of these layers. I think we were at slide 37 somehow. Yeah? So what are the tasks of these different layers? So for some layers you have an influence, you can do something. For others you can't, because everything is handled in hardware, like L1, L2, L3, everything is handled in hardware. Huh? Between main memory and storage devices like disk and SSD, we have some influence, and that's typically where database people jump in and do something about that. So how to implement those layers depends on the physical properties of the layer, capacity, access time, bandwidth, its interaction with other layers, and what we want to do with the computer system. Yeah? So the task I want to execute on such a layer may have an influence on how I implement such a layer, if I can do anything with the implementation. Yeah, there's one important divide, or two kind of classes of problems you can look at. So one is a general purpose storage layer implementation. So the idea is that you implement the storage layer with a goal to support a very diverse set of applications. An example for that is the paging mechanism that's in a Linux operating system or in any other operating system. Yeah? The operating system has the same problem. You have data on disk, and you eventually have to load it to main memory. Yeah? And if the memory is full, maybe you have to evict data from main memory and write it back to disk. But of course, on your Linux operating system, you can run any application that runs on Linux natively. The same for any Windows, Mac OS operating system. So you're not saying this, that you don't write an operating system just to support a single application. You don't write an operating system to only support Google Maps. Let's phrase it like that. The operating system is written as general purpose to support any type of application you may ever think of. And the opposite of that is a domain-specific storage layer implementation. That's this one. So the idea is it's implemented with a goal to support a specific class of applications. So for instance, in a database, we will implement that database buffer in between main memory and storage, because the database is very specific. It makes very specific accesses to the storage layer. It is restricted in what it does with the underlying storage layer. And therefore, we can do optimizations that are not possible in the file system, because the file system is general purpose. We are domain specific. So that's an important concern here. Yeah, so that's what we looked at. It's just some idea on what you actually see in practice. It's a very old. So if you have a CPU like that, that's a very old one. I'm not even sure whether you get, maybe in an embedded systems you would get something like that. So the idea here was you have a CPU, here you have a core, then the CPU, typically, then you have the different caches, L1, L2, L3 sitting on that CPU. And there's a board where you plug in the CPU, and on the board you also have main memory. And then there's some flash or hard disk, either attached through an interface that's called SATA, or sitting directly on the PCI bus, in particular for flash memory. Most today, data sits directly on the PCI bus, typically. But you could also do something like that. So that's called a multi-core storage hierarchy. And here you see we have 4 different cores, plus each of those cores has its own L1 and L2 cache. Then there's a shared L3 cache, and then everything else here is the same as before. I'm just saying, okay, I'm replicating the number of cores. And that's a multi-core architecture. Here's another architecture that's very common in data management. Here you see that we have, so in contrast to the previous, there was still one CPU. One CPU consisting of 4 cores with their own L1 and L2 caches. And here, in the next image, we have 2 CPUs. Each, like on the slide before, has 4 cores. So in total, we have 8 cores. For each CPU, we may have a separate memory bank attached to it. So we have on the same layer, conceptually, 2 types of memory And in this kind of architecture, that leads to the phenomenon that access from here to there is slightly faster than access from here to there. Yeah? Here you go along a larger bus on the hardware. It takes some more time to get there rather than here. And that is why this architecture is called a non-uniform memory access. Non-uniform in the sense it depends on which type of main memory you're accessing on such an architecture. Yeah? If it's the main memory here, everything is fine. It's the fastest you can get. But here it's slightly slower. And that means in these architectures you have to worry a little bit how to partition your data and how to place your data into main memory. Okay. So, and the interesting thing is, and you don't see that too often in practice, is, well, now if you think about, okay, what is the network, what is the internet, what is any server on the internet? Well, if you learned about the storage hierarchy, you could actually say, oh, well, that's just another storage layer. There's no difference whatsoever when talking about the internet. So basically, we could also draw it like that. Yeah? That is now our computer, yeah? Having access to several storage layers. Yeah? So the purple box showing what that was a previous slide, and I'm saying, okay, then it depends. Access times may vary on the internet. If the servers in Frankfurt or Kaiserslautern or here in our server rooms, access is relatively fast. Yeah? If it's in Iceland, it's a bit slower, US even slower, on Mars even much slower. So it's the same phenomenon you see. The further you go out, the slower is the access, and bandwidth will typically also decrease the further you go out. Yeah? Yeah? Understand the idea? So why would that make sense to present the internet like this in such a graphic? Why am I doing that? Yeah? Does it mean that Frankfurt server, what? Depends on the Iceland server. Yeah, okay. If you have the inclusion property, yeah, the inclusion property means that whatever you, when you have something stored here, it's basically a subset of what is stored there. Yes, it's always for each layer on top, you only load a subset of the stuff that's stored underneath. Yeah, that is kind of broken on the internet, of course, because it's not only one server on this storage layer, but there's so many servers, yeah, and they have the same distance in terms of access time as latency. You call it latency on the internet. Yeah, that's true. That may happen. Yeah, but I mean something different. Why would it make sense to put all of these things into one common storage hierarchy picture? For what reason? Why would that help? Yeah?
Maybe because every server can get the data from maybe another server. So maybe one server loses some data. They don't have to request the data from the core. So
Yeah.
they can just request from another server, and maybe that's a bit.
Yeah, there's replication happening all over the place. Yeah, so if the data is not available on the server in Frankfurt, you may request it from Iceland. If the data is not in Iceland, maybe it's in the US. If it's in the US, you load it to Iceland, load it to Frankfurt, and then you can keep on loading it upwards. Yeah? That's the same idea as in the standard storage hierarchy we discussed here. Yeah? So whatever you have in L2 should also exist in L3, main memory, and flash, and so forth. Yeah? So whatever is available upwards in the storage hierarchy towards the core is also available on the layers underneath. It's called the inclusion property. But my question is more like, okay, now this is what you see in textbooks, okay? Now I'm saying, no, why not write it like this, or write it like this is one huge storage hierarchy? Why would that help you in designing systems, understanding systems, yeah, reasoning about how to transfer data in such a system? Is that, can you see it even? Should I make it? It's a bit more colorful. Yeah, why does it make sense? Which principle did I apply? We only had one principle so far, right? It's a laziness principle. Yeah, I try what I learn or what I know. So I grew up as a database researcher with the stuff here. Yeah, now I'm saying I map all of this network stuff to additional storage layers, and then what? What does that allow me to do? Yeah.
You use all the logic you have for L1 and
Yeah,
so on.
exactly.
Same,
All the techniques, all the algorithms, everything I ever learned about this storage hierarchy I can now apply it here. And guess what? All these techniques exist. Yeah, whether, yeah? I speak up louder. I don't understand anything. The speaker's
Isn't
mask.
our laziness costing us time now? It seems rather stupid to load something from the server in the US to Iceland to then get it to Frankfurt. Because those don't work like the internal system architecture. We're now doing irrelevant operations.
No. I'm just saying in principle, it is like that if something is stored, so the storage hierarchy, again, the inclusion property means if something is stored here, it's also available on the lower layers. That's the inclusion principle. If you now want to design a system that guarantees quick access time, like a Netflix, Amazon Prime, yeah? You watch a video and you want to be able to access the video streams quickly, you will rarely hit a server in the US on Iceland because they have copies stored locally, which means the data sits on servers in Frankfurt or even closer by. Yeah, but still, you have copies of the data further away in case anything goes wrong here. But there's no difference to what we learned so far in the sense that we have the inclusion principle and stuff gets cached on higher levels. That's another term for that, caching the data. Yeah? So you cache data in main memory, meaning you cache data that also lives on disk in main memory. You cache data on the server in Frankfurt, which is also data available in Iceland, for instance. Does that answer your question? Yeah? So how I exactly cache the data is a different story. Yeah? But again, the important thing is by mapping it to a known problem, I can now apply all the stuff, all the algorithms, the database buffer management, replacement strategy. It's the same stuff. If you ever attend a network class, you will see, hey, it's the same stuff. Often it's different names. Often things are separated across different communities. That's another phenomenon. So you will have a computer science community called networking that handles this. There will be a community databases handling this. There's a hardware community handling this. Yeah? And they all use different terminology, of course. Otherwise, it would be too easy. But by mapping it, you are able to extend your toolbox. Yeah? So the key questions we will be looking at now is, so first was how to store, access, and query the data. And for this concrete application, it's where and how to store and cache the data. Yeah? So the how part of the question has a lot to do with how to transfer data in between those layers. I'll skip over that notebook. So the slide set we have here is for designed for 3 lectures, but this year we are only doing 2 due to this guest lecture. We only have 2 lectures. And one thing in such a scenario in Google Maps to worry about is data compression. And data compression can be used in 2 different ways. You probably only know one of those. So one is to compress storage space. Yeah? You have a large file. You want to save space on disk or wherever you want to store it. So you compress it using zip or whatever compression algorithm. Yeah? So you probably have seen zip. You have seen a JPEG file. JPEG is a compressed format. Basically all video formats are compressed in one way or the other. The other application of compression is to save bandwidth. Yeah? So we want to transfer data from one storage layer to another, maybe from the server in Frankfurt to our machine. And the idea is I want to save that bandwidth. So assume you do a children's birthday party and you need these air balloons for the party. So you can order them with a delivery service. And how are these air balloons delivered? They're not inflated at the factory. In fact, they are deflated and compressed like crazy, put in the parcel, then shipped using the delivery truck. Then you get the parcel with the air balloons and then you inflate them. Yeah? Think about a moment how stupid it would be to inflate the balloons and then put them in the truck and then deliver them inflated already. Maybe you can even buy this stuff inflated, I don't know. It's worth checking it out, yeah? But it's the same idea as here. If you have something that can be deflated, before shipping, you first deflate it, put it on the truck that is sending it over the wire to the next layer, and then you inflate it again. That's the same idea here. Yeah, so, and with that, here are some examples for uncompressed data and compressed data. You see it all over computer science. So uncompressed is this, bitmap, TGA is an image format, raw is an image that is generated by digital cameras. That's the raw information collected by the sensor versus JPEG. Huh? If you have a digital camera, or even the smartphones, they can also do that. Yeah? You can always pick whether you use raw and JPEG. Many people only use JPEG. If you've never tried RAW, give it a try. It's a huge difference in quality because JPEG is compressed like crazy, for instance. Yeah, and there are other domains where you see it frequently. WAV is an audio file that's uncompressed, compressed basically sampling like every, whatever, 20,000 times a second. Where is my audio signal currently? And then writes down a digital value. Yeah, those files get big, so eventually people devised a format that's better, like MP3. Yeah, MP3 was relatively small at the time and allowed people to come up with different applications like streaming or distributing MP3s over the internet, which was difficult at the time because the internet was much slower. It had a much smaller bandwidth. And the same holds for all kinds of other formats. Good. Yeah. Then if you look at Google Maps, now we see that the format they use is PNG at least for OpenStreetMap. So I will talk a lot about OpenStreetMap because that's kind of the open variant of Google Maps. Google Maps is not really accessible to me. Yeah, you can embed a map, of course, on a web page and stuff like that. But I want to have a better access, and so there's OpenStreetMap, and that uses PNG files, which are compressed. And now the kind of math you can do with these kinds of things is you think about whether compression makes sense. It makes sense. Sense. So the simple equation we do here is we want to compute the transfer time to send n bytes from storage layer X to storage layer Y. And if you have something like the bandwidth is like, for instance, measured in gigabytes per second. The math is relatively simple. You just divide it, n divided by this BW, then we get the number of seconds it takes to transfer n bytes from storage layer X to storage layer Y. Yeah? Simple calculation. And in the following definitions, I assume that the time to read data on storage layer X or to write it to the target layer Y is not the bottleneck. Yeah? That's not limiting what I'm doing. I'm just talking about the actual transfer time. So the truck on the road, how long does it take to get from X to Y? And if you make a simple example, let's assume we have 1 terabyte of data. And the transfer time is the bandwidth, in other words, is 10 gigabytes per second. Well, obviously, you take 100 seconds to compress that data. Yeah? So easy math. Now, if you think about how long does it take to transfer compressed data, that's this calculation. Now we have 3 components. This is the one we had before, however, with an n subscript c, meaning that is a compressed data stream. So the idea is, you have n bytes, you first run those n bytes through a compression algorithm. Yeah, it's basically the inflated air balloons. You put them on the floor, let's hope they're not, you basically open it, yeah, all the air goes out, and then you put it on the floor and stamp on it a little bit to deflate it a bit more. That's a compression algorithm. Then you transfer the compressed algorithms / bytes. Yeah, that's again the delivery truck. And once you're at the target, you inflate them, the balloons. Blow them up again. And that's a decompression algorithm. And here the input, note that the input is NC, so the number of compressed bytes. So all of these things add up and give you the time to transfer n bytes using a compression and decompression algorithm. Okay? So now what we want to find is something like this. So we want to find a time that is actually smaller than transferring uncompressed data in the first place. And that depends on many things. So the data compression ratio. So how much can I deflate the balloons? Yeah, what is the factor? Is it 5 times smaller, 10 times smaller, whatever? My runtime of the compression algorithm, how long does it take? You don't get that for free. Depending on the type of compression, that may take longer or shorter amounts of time. The same for the decompression algorithm. Typically, this is asynchronous, so often it's like compression is a bit more expensive than decompression, but it depends highly on the algorithm, the compression algorithm being used. Yeah? So here are some examples. This is what you saw before. Yeah? Without compression, 1 terabyte, 10 gigabytes per second bandwidth, well, that's 100 seconds, yeah, like above. And now I have 2 examples with compression, with different compression algorithms. Let's assume this first example, compression time is 1 gigabytes per second. Decompression time is 5 gigabytes per second, and the compression ratio is 5. Now, if you do the math and put it into the equation above, okay, 1,000 gigabytes compressing with 1 gigabytes per second is 1,000 seconds already. Wow, that's a lot, right? So then you transfer less data. Yeah? As you have a compression ratio of 5, it's 1/5 of the original terabyte, so 200 gigabytes, the compressed data stream has to be transferred. So you save something here. This is only 20 seconds. That's cool. And then you decompress it 200 gigabytes with a speed of 5 gigabytes per second. That's 40 seconds. So the overall thing is, the overall time is 1,060 seconds, which is obviously bigger than the original 100 seconds. So this kind of algorithm used here does not make sense. You don't gain anything. It takes more time. I mean, you gain something in the sense that you transfer less data. Yeah, maybe if you have to pay by the amount of data being transferred, like in a cell phone contract or something like that, then you would gain something. But in terms of time, you don't gain. You lose. It takes much longer in this example. Now let's look at an example with inexpensive compression. So assume we can compress 50 gigabytes per second, decompress 100 gigabytes per second. However, we pay a price, the compression ratio is less. Yeah? That's a typical trade-off you see. The more you invest, the more the compression algorithm invests in terms of CPU, the higher the compression ratio. The less you invest, okay, you don't get that such a good compression ratio. And you see this divide here already in this example. Huh? So if you do the math, now we only need 20 seconds to compress this stuff. Then we transfer 333 gigabytes, decompress it, and we get a total time of 56.6 seconds. Yeah, and that's somewhat smaller than the 100 seconds. So that's an example where we gain something in transferring by using the right compression algorithms. Huh? So this type of sweet spot is what we try to achieve in these examples. Yeah, but let's look at some extensions of that. So how can we improve this compression transfer time, even for a subset of the non-beneficial scenarios where the transfer time of the compressed algorithm, TRC, is greater, strictly greater than the transfer of the uncompressed data. So what I mean is, so assume we are in a scenario where we do this kind of back-of-the-envelope calculation, and we get something like that. Maybe not that extreme. Eh? Maybe that is hard to fix. Maybe or not. Is it fixable? How could you fix that? Yeah, let's make it more concrete. Under which conditions would this actually work? And would be beneficial? It would be better than transferring the uncompressed data in the first place. You were first, yeah? If we make something available for download, yeah, what would that imply?
Well, we have the time it takes us to compress it. It doesn't matter. We just care about the time it takes the person downloading it to decompress it.
Yes, right. So the idea is you compress it before the request comes in. Yeah, there's a typical scenario is a one-to-n relationship. There's a file that's downloaded very often. Yeah, you only have to compress it once. You don't have to compress it for each and every request coming in. You compress it once, and then with that you remove that timing from the equation. Yeah, you still have to do it, and you could, okay, divide the effort, we call it amortization, over the different requests, okay, but if you say that doesn't count for the individual request, you basically can remove that, and then you're down to 60 seconds. That's less than 100 seconds. Yeah, so you could do that before. It makes a lot of sense in all kinds of scenarios where there's video, images, stuff to be downloaded multiple times. Makes a lot of sense. So that's A. A is correct. Yeah. What is with B? When receiving the compressed data, do not decompress it, then do whatever you want to do with the data on the compressed data. Yeah, so that's basically trying to attack the thing in the middle, no, not the thing in the middle, it's trying to attack whatever you do with the data on the receiving side. Yeah, I would assume you decompress it. So in the equation, we would basically kick out the decompression part because I'm saying, whatever, I don't need to decompress it. I can work with the decompressed data in the first place. No need to decompress it. Does it make any sense? If yes, why? If no, why not? Well, you can make a wild guess, right? So, who believes B is right? Who believes B is wrong? You said yes and no? No, right? It depends, okay? Okay, so no. Who said no, and why would you say no? Yeah, maybe you? Okay. Yeah.
To install something, we need the data unpacked.
Mm-hmm.
If we just want to use some file, like in Linux, you can also access it without decompressing something. But in other cases, it would be pretty useless.
Mm-hmm. Good comment. Okay. Other comments? Who said no? I don't remember who said no. Anyone wants to add on that? No? Or who said yes? You want to say something? Didn't you say yes? Yeah. Yeah, you.
Yeah, I said both. Maybe it depends on what the data is used. Maybe it's used in the context where the compressed data is enough, then it makes sense to not decompress it. But if we want to get the data, but when the data has to be very specific, or where we need all the data that is coming from the decompressed data set, then we have to decompress.
Yeah, good. But the interesting question, why would it make sense to not decompress it, right? What scenario could that be? If I don't have such a scenario, this doesn't make sense, answer B, yeah? As you said, because I have to decompress it, yeah?
Maybe there are different kinds of accesses, so for some you need high quality, for others it doesn't really matter. For example, image quality,
Mm-hmm.
you want to do some add-on and maybe you need every pixel and every bit of information, whereas if you're streaming some movie,
Yeah.
you don't really need the maximum quality.
But you're assuming the data is streamed in both types of quality, low and high, and you jump over certain parts to just extract whatever you're interested in and then decompress that part. Something like that? Okay. Mm-hmm. Yeah, someone else? So back to the air balloons. So again, they are already compressed in the fabric, no time wasted, and they're shipped by the truck. But what if I use them as a sling and you teach children to sling them at each other without inflating them in the first place? You ever tried that out? Yeah, just, yeah, something like that. So the answer is right. It depends on how you want to use it. And with what you know, you would probably, it's absolutely fair to assume no, it's not possible. I would have answered the same thing in the first semester. But there are actually algorithms that allow you to do that. I learn about them. We did that actually, I think last week in the database systems core lecture I'm teaching currently. That's 5th semester and on. So when I ask the same question there, it's a little bit more split, yes? There are more people saying, yeah, it's possible, but if you've never seen how that works, yeah? So the answer for the moment is yes, it works. Yeah? There are situations where it's possible, not in the general case, of course. Yeah? It depends on the type of data you're sending, the type of compression algorithm, but there are cases where that actually makes sense. So let's look at C. What if we overlap compression and transfer? What do I mean by that, overlapping? Do you understand the question? I'm not sure whether it's clear. Yeah, if you look at this formula, so what I'm saying is, okay, this is like calling a function in Python, yeah, with the n bytes. Eventually, the function will return and give me those n bytes, compress the nc bytes. Yeah? Once I'm done with the function, I will call the transfer function, which will transfer the nc bytes. Once all of those are received on the receiving side, I will call the decompress function. So in terms of timings, this means there's one component here, a time component, a second component, and a third component. You add them up and get the total time. Okay? So that's how you could understand the formula. And now the question is, what if I overlap? So overlapping means, is there any way that some of these functions can be executed in parallel to save some time? That is the question. How would that work? Yeah?
Can I give my opinion in C?
Can you speak up louder? I can hardly.
Can I give my opinion of C and D at the same time? I think C will be possible in most cases, unlike D, because you can start sending the already compressed part of the file most of the time. Although decompression, I think for most files has some number and that needs the complete file for it to work correctly. So.
Okay. So he's saying for C would work and D probably not. That, yeah, whatever most means, yeah. Some other opinion? Yeah?
I think it's the thing that's commonly done by Steam. It's an application for the computer. While Steam is sending you some data, it sends in small packages which are compressed, send,
Mm-hmm.
and also for each one decompressed on the computer.
Mm-hmm. Yeah, it's a packetization. Yeah? The data is not sent as one big parcel, but in small parcels, small packets, and you can treat each parcel individually. Once you have received one of those parcels, you can already decompress it. Yeah, so here we are in the overlapping space already with respect to decompression. Yeah? Actually, it works for many algorithms. You can do these things in both on the compression and on the decompression side. Yeah? If you haven't done the compression ahead of the request, and you still need to compress when the request comes in, you can still start compressing and then stream the output over the wire, yeah? And then on the receiving side, you're already receiving the first streams and start decompressing it. So you have all three functions running at the same time, actually. Yeah? Still compressing while not everything was compressed, sending whatever is already compressed over the wire, and on the receiving side, start decompressing. So all these three components may overlap. Yeah? And then you just have to look at the bottleneck. Okay, good. So those are the key questions with Google Maps. So how do we make query processing efficient and scalable? We will look at some examples. We look at two-dimensional range queries and how to make that happen for just any kind of data. There are different types of data, different classes of data, if you wish. There's satellite data, and there's roads and borders. That is vector data. Yeah? And what is the difference? Sorry, it's still in German. So raster data or satellite data on the right, those are basically the images you get from the satellite. Pictures, be it 2D or 3D, here it's 2D. Basically what you get from a digital camera. Whereas those vector data, you see it here on the left, those are idlest data items, only consisting of polygons, lines, and texts. Yeah, so you could also see it like that in raster information. You basically have such a grid. Yeah, the same as for any image format. You have a huge grid, and each cell in that grid is called a pixel. Yeah? Your camera takes pictures like that, and then the pixel has a certain color in RGB, yeah? A certain color value. Here, if you zoom into a picture, you will see this grid pattern appearing if you zoom in a JPEG or any picture format. This is not true for the vector data. Basically, if you want to define a line, if you wanted to define a line here, you would have to write down all the appropriate pixels to form that line or form any geometric pattern in the raster data, whereas on the vector data, you just say start point, end point, there's a line. And that has the effect, if you zoom in and out on vector data, there will never be an artifact. It will ever be perfectly smooth because it's just mathematically defined. A line can be defined mathematically by start point and end point, 2 points, triangle, 3 points, and so forth. So that's vector data. And you have both types of data in Google Maps. Yeah? So it's a combination that you can switch on and off those layers. Yeah, and with that, we need some definitions to facilitate the further discussion. And this is basic terminology from the database domain. You will see why that makes sense and why it gets important. So the first is what we call a domain, or in German, it's a Wertebereich. So a domain D describes all possible values of a variable. Now, when you make an assignment in Python and say a equals 42, yeah, you use an integer. Yeah? And if you look at if you make a equals 43, 45, whatever, those are all integer values. Yeah? You have floating values, dot, whatever values. But if you look at the domain, the integer is a domain. So it has a certain set of possible values that may occur in that domain. That's what I mean here, Wertebereich. Yeah? So examples for domains are integers, float, string, all kinds of enumerations. So sometimes you have very small domains where you explicitly enumerate the possible values, female, male, diverse, for instance. You can make restrictions. You could say, so possible values are only the integers smaller than 42. Or you can even use structures, structure types like JSON, the graph, any byte sequence, and so forth and so forth. But we don't need that for the moment. For the moment, the first three are the interesting ones. Yeah, then with that we get to what's called the relational model that was invented in the 70s. And in all my lectures, I stick to the notation you find in this book. We will look at that book or at that material in detail in the big data engineering lecture in the 4th semester. This is just a little outlook on what is handled there. So following definition, we have a relation. A relation is a subset of the cross product of n domains. Yeah, if you take n of these domains and put them together using cross products and then take a subset of that cross product, we call that a relation. Every tuple that corresponds to this expression in the number of attributes, so here I have n attributes in the tuple and here I have n domains, and if I take such a tuple from such a relation, that's what I call a tuple. Yeah? So this concrete attribute values, that could be 42, 7, 8, 9 in the string, whatever, that is a concrete tuple I take from such a relation. These individual values are called attributes or attribute values for short. Yeah? So basically you could also interpret those domains as they somehow represent attributes. For instance, they may be representing whatever. If you think about this, could be students, that could be the first name, then there's a last name, then there's a student ID or something like that. Yeah? And if I take any element from such a relation, that is then a tuple. Important is the order of the tuples doesn't matter at all. You may not exploit the order in any case. And to facilitate matters, we extend the definition to a so-called relational schema. In a relational schema, we specify both the domains and the attribute names of a relation. Yeah, so you see the difference here. That's the definition. Again, the notation is like in the Kemper book. You see the domains as above. However, I write in front of a domain, I always write the attribute name. So for instance, let's look at the example. Assume I want to represent cities of some sort. Yeah, then I always write attribute name, colon type, attribute name, colon type, and so forth, and so forth. Yeah? So with that, I could represent cities if those are the attributes I'm interested in. No? So we have a name of the city, we have latitude, longitude, inhabitants, if that is what I'm interested in. Again, the order of the attributes in a relation doesn't make any difference. The order doesn't matter. You just define it once and for all, but you only refer to those attributes by their names and not by their position, typically. So that is the relational schema. And now if you look at Google Maps again, where that makes sense, well, you can identify these different zoom levels. Yeah, if you play with Google Earth or Google Maps, you see, okay, you start maybe here on the left. Yeah, then you zoom in and you get this map. Yeah, that's what this is supposed to show. And you zoom in further, then you get down to the Saarland area, and then you get down to our campus. And I think you can zoom in even further. So basically, what you're seeing is you have data in different zoom levels available. Yeah, and depending on the zoom level you're currently in Google Maps or Google Earth, the database has to deliver to you the right data. Or the web server behind Google Maps or OpenStreetMap has to give you the right data, the right images in order to show you the correct map for that specific zoom level. So, and what that means is that on each zoom level, so if that is an arbitrary zoom level here, there are multiple of those images. Those images here are called tiles. Now that's one tile, there's another tile, not T-E-Y-L, but T-Y-L-E. That's the spelling, a tile, like on the floor or something like that. So there's a server that allows you to retrieve those tiles. You can say, okay, I want to have a zoom level X and then a certain region on the planet. Please give me all appropriate tiles for me to display. Yeah? So that's a mechanism you need in such an environment. Yeah, and then you can do some calculations like, okay, assume on one specific zoom level, assume that assume that you have 10 kilometer width. This is in German, this is a bit nasty, sorry for that. But basically, what the slide is showing, of course, the more you zoom in, the higher is the number of tiles, and it increases with the square complexity, of course. Yeah? Because if you have a certain resolution here in one dimension, assume it's one tile is 10 kilometers wide and 10 kilometers high, yeah, then one tile would cover 100 square kilometers, where if you zoom in, yeah, and increase the resolution per dimension times 10. That is what's happening here, yeah? Times 10. So here, one side would be 100 kilometers. Doesn't perfectly map to the, correspond to the map here. This is more in the true map. But conceptually, yeah, if you increase the resolution in one of the dimensions, as you have two dimensions, you increase it 10 to the power of 2 times. Yeah? If it were like a three-dimensional thing, three-dimensional system, you would increase it by 10 to the power of 3, of course. The number of tiles would be increased like that. Yeah? So if you go down, each of those tiles on the next level is represented by 10 times 10, so 100 tiles in the next resolution. I don't know how Google does it, what the factor is in detail, but in principle, you have to have something like that. Yeah? There will be more tiles on the higher resolution level, and you will see that when we look at OpenStreetMap in a moment. So the relational schema for this Google Maps scenario looks as follows. So we have a tiles relation, and it has the following attributes. So we have an ID. So ID, typically you see in those schemas, are unique. Yeah? So for each tuple in such a relation, you want to have a different ID. They're all pairwise different. This is also called a key or primary key in database, but we don't go into that detail for the moment. We have a zoom level. We have an X position, a Y position, and a path on disk to the corresponding file representing that tile. So the zoom levels are defined from 0 to a max zoom level. 0 is the lowest, max zoom level is the highest resolution. X position is the offset of a tile in X direction, Y in the Y direction, obviously, file path, image on disk, as explained. And the X position is in this domain. So from 0 to 2 to the power of zoom level minus 1. So what I'm saying here is that with every zoom level, I double the number of tiles in each direction. So when I start with an initial zoom level of 0, I have a single tile. Zoom level 1 has 4 tiles, and then always times 4, 16 tiles, and so forth and so forth. I always split it in half, basically. And by that, I double the resolution per dimension, which means I quadruple the resolution per zoom level. Okay, that's basically the number of tiles you can compute like that. So 4 to the power of 0 is 1 tile, representing the entire planet, one image in the most coarse granular resolution. First zoom level is 4 tiles, second is 16 tiles, and so forth and so forth. It gives you that many zoom levels in total that you should keep in your system. Yeah, and now we need to define what we mean by query. So if you have data like that stored in relations, that's typically done in something that's called database system, and then we want to be able to query the data, which means I don't want to have all data, I only want to have data that fulfills certain conditions. In order to allow that, I define a query expression that's using this Greek letter sigma, and that's called a filter query or a selection. So the idea is, you can read it like a function, basically. So the input is your relation with all the data, and the return of that is again a relation. And what this function is saying, return all elements from R where each tuple in the return fulfills a certain predicate. A predicate is a special function in computer science that only returns true or false. So general functions may return anything. A predicate is restricted in the return type to Boolean. That's only true or false is possible. Then we call it a predicate. So basically, what you want to do is you look at the input, you inspect each tuple. If the tuple fulfills the predicate, you put it to the output, which means whatever you do in such a selection, you can only end up with a subset of the original input, because you can only remove tuples. You can't add a tuple. It must be a subset, or it can also be equal if you don't remove any tuple, if all tuples get through. So an example would be a predicate would be something like that. So where the zoom level equals 2, this should also be an equals, of course. So if the zoom level equals 2, then the tuple should be sent to the output. This is also called an equality predicate. So basically the pattern you see here is that you have an attribute name here in the predicate, and you have a certain constant on the right of the equals condition. Yeah, okay, so with equals. In the programming language, you typically write equals. In databases, you only write one equal, because here it's clear that this is a comparison and not an assignment. In the programming language, it's important to make the difference, because if you write one equals, it's an assignment to the variable on the left. But here it's not an assignment, it's really a condition. You would write it as equals in the programming language, including Python. So here, so where am I? Right, so this is equality predicate saying, okay, this attribute name, that's an attribute name in the input relation tiles. If you go back, tiles has certain attributes, and one is zoom level. That's the attribute name. And now I want to make a equality predicate, or point query as we call it, on that zoom level, saying, give me all the data, all the tuples where the zoom level equals 2. That's basically the idea of that. So the input is a set of tuples, we call it a relation. The output is a set, it's again a relation, a set of tuples that fulfill a certain condition. And with a selection, like explained on this slide, I have a condition for each and every tuple in the output, phrased as a predicate. So that's a condition to the tuples that are part of the output. Okay, so then when you look at how do you compute this stuff, just for you to give you an idea on what's possible. So there are basically only two options. Whatever you do, there are only two options. So in the end, we want to have this function, or we also call it an operator, return this set of tuples qualifying under the predicate. Well, and the easiest way to do that is, of course, we can test each and every tuple from R. Yeah, basically like a loop. For each tuple in R, if the tuple fulfills the predicate, send it to the output. Yeah? You loop over the input data, which means you inspect each and every tuple in the input. Yeah, that has a linear complexity, so you have as many operations as there are tuples in the input. However, in practice, that's not the best thing you can do. What you can do instead is you can use what we call an index, or you will also learn about that in the undergrad lecture, Data Structures and Algorithms. So index is database language for data structure. The idea is, high level, we organize the contents of the input relation such that if the query comes in, we don't have to inspect each and every tuple. We only have to inspect the subset somehow. However we do that, yeah, there's a way to organize your data such that you don't have to go through all of the tuples, but can inspect the subset, and that is obviously faster than inspecting every time those many tuples in the input. Okay, and we look a little bit at what that actually means. We don't do the entire slide set because we have time for that, but to give you an idea on how that works. For that, we need the term horizontal partitioning. So horizontal partitioning means you have an input relation R, as defined above, and now I split it into chunks. Now, each of those chunks is again a relation. I have relations from R1 to Rk, and I call those relations horizontal partitions of R. The important property is this here. This is saying whatever tuple existed in the original partition R, it must now exist in one of those horizontal partitions. I can't just leave it away. Yeah? I basically, each tuple I take from the input relation R, I have to put it to one of the RIs. It has to be in one of those horizontal partitions from R1 to Rk. And those RIs are called horizontal partitions. So here are some examples. Yeah? If this is your input relation, and the schema just consists of, so this here was a schema with, we had 4 attributes, 1, 2, 3, 4, with 5 attributes. Now we're looking at a simpler schema to explain matters with 2 attributes. And you see we only have 4 tuples here, those 4 tuples and their color to make the discussion easier. And now I could partition that. I use horizontal partitioning, and then you have a partition R1 containing those tuples, R2 containing those tuples. That is a valid horizontal partitioning because all of these tuples got assigned to subpartitions. Yeah? That's valid. No tuple was left out. The same holds for this one. Yeah, that's also okay. This here is not okay because the red tuple 7, B was not assigned to any of the sub horizontal partitions. Yeah? So that's not a valid horizontal partitioning. I can make that, I can extend that definition to make the partitions disjoint, and that is the following definition saying, okay, a horizontal partitioning is called disjoint if all pairs of those horizontal partitions do not overlap. So if I intersect any of those horizontal partitions, I receive the empty set. Yeah? In other words, if I take a tuple from the input, I must assign it to exactly one of those horizontal partitions. Yeah? So this definition is saying it must be assigned to at least one of the definitions, and this definition is saying it must be assigned to at most one of the definitions. The sum of those definitions makes it, it must be assigned to exactly one of those partitions. Yeah, do you see that? Okay, we are hearing Prog 1 and Mass 1, this is probably... Okay, yeah, so this is an example for that. Yeah? This is not a disjoint horizontal partitioning, of course, because this tuple occurs in both of the horizontal partitions. Yeah, so much about that. And now with that, we can define a partitioning function. So what is a partitioning function? It maps from an input schema from a relation R to a domain D. And let's start with an example again. So here's a partitioning function defined as follows. The input is a tuple, and you return the value of t dot a modulo 2. So if you divide t dot a by 2, what is left over? Yeah? So in other words, this is giving you the information whether it's an odd or an even number. If the return is 0, it's an even number. If it's 1, it's an odd number. Those are the two possible return values here of this function. Yeah? And then you see, okay, if you input 2, also the entire tuple is being input, of course, in the function, but then you access this a attribute. Okay, return is 0. Here for 7 it's 1, for 1 it's 1, and for 6 it's 0, and so forth. That's one way of partitioning the data. Here's another partitioning function that's defined on attribute b. It just returns the character that is in attribute value b. So basically you return a, b, b, c. Yeah, those are partitioning functions. Now we have horizontal partitions, horizontal partitionings. Did I call them partitions or no partitioning? Yeah. And we have partitioning function. If we put the two together, we can define an induced horizontal partitioning. What does that mean? Given a partitioning function, the horizontal partitioning of R into its partitions Ri, such that for all tuple in the original relation R, T is contained in the horizontal partition where the subscript, the label of the partition, corresponds to the return value of the partitioning function. That was a long sentence. Yeah? Let's look at an example. So basically, that partitioning function can only return two different values, 0 and 1. And now I use those values as labels for the horizontal partitions. Yeah? So there can only be two labels, 0 and 1. The result, the induced horizontal partitioning is here. So the subpartition with the label 0 contains the even t dot a values, whereas the R1 partition contains the odd t dot a values. Yeah? That's basically a partitioning that is induced or implied by using a certain partitioning function. So it's not, as we did it before here, when I introduced partitioning here, I said, okay, yeah, there's some relation R, and I somehow partition it into those subpartitions. Yeah, that's how I did it here. That's not what I'm doing on this slide. Here I'm saying, no, I automatically generate those partitions based on the outputs of those partitioning functions. Okay? Yeah?
Could you maybe explain the horizontal part of that?
Yeah. Excellent question. Excellent. Yeah. Okay. The horizontal is because. Okay. Yeah. Super. Okay. With what you know, horizontal doesn't make sense because I was only talking about sets. Yeah, a set is what is a set? There's no order in a set. There are no duplicates in a set. There's no, let's say, geographic representation of such a set. Yeah, it would be arbitrary. Yeah, you can represent it somehow. Horizontal comes from database terminology because once you try to implement a relation, you end up with something that we call a table. Yeah, and that basically means you give the elements in the set an order. Now, one underneath the other. Yeah? Tuple 1, 2, 3, 4, 5 in a table representation. And what the horizontal partition does is it chops this table into horizontal blocks. Yeah? If you think about this horizontal representation, and that's where the name stems from, horizontal partitioning of the table. But what's meant is a partitioning of the set where horizontal doesn't make too much sense. You're right, yeah? Yeah, that's an old term, kind of. Yeah? There's, of course, also vertical partitioning that's along the attributes. But here we look really, basically, if you stick with the set semantics, it only means you divide the set into subsets. And you can leave away the horizontal if that helps you. Yeah? Yeah? Okay. Okay, so where was I? Ah, no, I was still on this slide. That's one. Yeah, so I'm also doing it here on, for the others. For the other partitioning function here, partitioning on t dot b, then I get 3 different horizontal partitions. Yeah, A, RB, and RC, and so forth. And what I could also do is I could do this recursively. So basically I could use both partitioning functions at the same time. So you see that here. So I first divide the data along the first partitioning function across the modulo return value, and then I split this R0 partition again into 2 horizontal partitions based on the second partitioning function. Yeah, so I could define an order of partitioning functions and recursively split my data with those functions. So why are we doing this? Well, the idea is, in any index, that is the idea, or any data structure, that's the idea, that we define such horizontal partitioning functions that can be exploited by a query to reduce its search space. So let's look at an example first before we look at the text above. So again, assume we have this partitioning. Yeah, this recursive partitioning using those 2 functions as defined above. And now assume you have a query like this coming in. Yeah? Filtering, you want to have all tuples where the attribute value b equals the character c. So select all tuples where attribute b equals c. So basically you could write it like that. Yeah? You take the input relation R. This is a correct expression, but you could rewrite this expression to this expression, where the input is the partition R0, C. Why is that correct? Yeah, because you know if a tuple's B attribute value is set to C, to the letter C, it can only live in this partition. Yeah, it cannot be in any of the other partitions, so it's fine to just use that as an input. Yeah, you will receive exactly the same result as calling this function in the first place. Yeah, does everybody see that? Yeah, I'm just as an input for the selection operation here, I'm using a subset of the original tuples, and the subset is chosen such that the result will be the same. However, the subset is smaller. Now that's the main idea here. And then depending on what the query which query comes in, you could say, okay, if A equals 7, well, that it would be this query, but I have that partitioning function modulo 2, so if I apply modulo 2 to the 7, I receive 1. So basically I can rewrite that to look at partition R1, B. Same applies here. If you have A equals 8, well, I have to look at all the partitions where modulo 2, also A modulo 2 is 0, so I have to look at all the 0 partitions, and I have 2 of those. So that's the union of those partitions that serve as the input to the query. There you go. Yeah, and the art in data processing is then to organize your relations and horizontal partitions that you can do these kind of rewrites. Yeah? On the high level, that is what happens in any data structure and index structure. Okay, I think we skipped some of those slides. I think we don't need them in the interest of time. Yeah, I just wanted to illustrate that a little bit with this example. If my laptop doesn't burn down here, it's getting very hot. So let's look at some notebook. It's a notebook indexing by recursive external partitioning. Here I'm partitioning a text file. And what is a text file? That's something I will use for the maps example. So I show you how it looks like. So this word count operation, so recall exclamation mark, and then you can write a command here, sends it to the underlying terminal, and the return is then integrated into the notebook. So basically, this is a word count on this text file. And when you look at the head of that text file, you see a lot of information. Here we have 3 tuples, each eats up 3 rows basically. So here's an ID, there's a name of that geographic place. You see the schema here underneath, so that's a ID. You have the name as a UTF-8, so that's a character representation allowing for stuff like the German SZ or the umlaute or Chinese and Korean, Japanese, whatever. And then there's an ASCII name of the same place with a double S in that example. Eventually, there's a latitude and a longitude. Okay? So why would this kind of data make sense for a Google Maps style scenario?
Those correspond to X and Y coordinates?
Yeah, X and Y, longitude, longitude. Longitude. It's written somewhere. latitude, longitude. Okay. Yeah, okay, but why would something like that, this data make sense? When you use Google Maps or any similar product, where could you figure that that data is used somehow? I mean, you just saw the images, yeah, when you scroll in Google Maps, yeah, zoom in, zoom out, see maps, display different layers. But this kind of data, this information about certain places, why would that make any sense? I mean, what happens if here I enter something like Washington? Yeah, what I expect is Google Maps will show me a zoom in to Washington. So it has to understand where Washington is. So there is a mapping from the geographic name to its position somehow. Yeah. So when I hit enter, what does Google do? It zooms into that area, Washington. Yeah. So it has a place, it has a geographic latitude, longitude for Washington, and then a window around that, and then it will select the corresponding maps to display the area. Yeah, for this kind of search index, you need that information. If you want to be able not to zoom in and out on a map system, but to write down a geographic name or a company name or whatever, then you have to have something like that. Yeah, and that is the index we are currently building. Okay. Yeah, this data is available for download. I also, here's the link, and I also uploaded it to our CMS. Oops. So. And what I will use in the following is not the mapping from the geographic, from the name. Yeah, you could also make a mapping from the name, not the mapping would also be nice, mapping from the name to its geographic position. Here, for simplicity, I use the mapping from the geo ID, yeah, from the geo name ID to its geographic position. That's another type of index, but you can define that arbitrarily. You could also say from name, from UTF name, whatever, alternate names, whatever. Yeah. And then I have a lot of machinery here. We don't have to look at this one. The interesting thing is, what I do is I define a partitioning function along the different digits of such an ID. Yeah, so if you look at a digit here, let's look at this one. Yeah, that's an ID, and the first digit is a 2. Yeah, so what I will do in the following, I will recursively, digit by digit, partition the different geographic places into buckets. Yeah, all entries that start with a 2 go into the 2 bucket, or with a 3 in the 3 bucket. And then I recurse. Within the 2 bucket, I will look at the second digit of the ID and recursively split it, and so on, and so on, and so on. Yeah? I'll show you how that works. I don't have to go through the code here. That's not the idea here, just to show you what the result will look like and why that would make any sense. So basically, I start with this comma-separated value here, file. Yeah? That's basically this text file. It's one file. And now I partition it into horizontal partitions or subsets, if you wish, that allow me to search specific entries faster later on. Yeah? And what this notebook does is it creates this file structure. So you will see originally the first partitioning step does this. It splits the input into those files. It seems like that certain digits are not available. So it doesn't seem to be any number starting with a 4. For instance, what else is missing? A 5 seems to be missing. Now I recurse. Yeah? So for each and every file, I create a directory, yeah, with a corresponding name. So everything that in the first partitioning step is put into this file will now go into directory 2, where the file name represents the second digit of the ID. Yeah? Simple recursive partitioning. Yeah? And then I partition, until I end up with things like that. So this file represents all entries that start with 11977. Yeah? And inside such a file, you may only find those entries. Okay? Yeah, and one disclaimer is, in practice, you wouldn't do this with text files. You can do it, but for performance reasons, you would do that with binary data, could do differently. I just want to show you how you could also exploit the file system for things like that. Yeah, here's a visualization of how that looks like. So basically, that is the index I created. And yeah, it's worth mentioning that if you do a recursion, you always have to decide whether you recurse further, whether you go deeper, or you break the recursion. I steer the recursion here in a way that I say, if the file, the resulting file, gets smaller than a certain cutoff, I stop the recursion. So as long as the file is bigger than this value, I will split it up again and do another round. Yeah? That is why you see this tree is somehow unbalanced. Yeah? So depending on the data distribution, you will see the tree gets deeper or shallower, depending on where you are in such a tree. Yeah? So that's the tree representation, just rotated by 90 degrees because that's easier to visualize. Okay, and now the interesting thing, of course, is when you search. That is basically the same thing. It's not exactly the same thing, but now you could say each of those CSV files is one horizontal partition. Yeah, and what is the label of such a file? That's the path along the tree, along the file system. So if you look at my index, yeah, that's how it looks like in the file system. And the interesting thing about the notebook is now you can use the file viewer to explore the index and explore the contents of the different files. And then you see what happens. So basically, when we open this file, you will see that this is all the stuff starting with 3. Okay. Now if we dig down, we say 6, 5, 5, and open 1. Yeah, you see, those are the entries starting with 6, 5, 5, 1. Okay, and so forth and so forth. Yeah, depending on how the data was created with those IDs, you have more, you have less files, but all those files have that certain cutoff. And now, of course, what you will do in query processing is, rather than searching through the original file, you will walk down the file hierarchy. So if I have a query like this, yeah, that's basically what this function is doing, is it starts at the root, at the topmost directory. So in other words, in this directory it starts, yeah, and then it maps my query to the file structure. Yeah? So it will check whether there's a 1.csv. If that is the case, well, I'm already done. I found the right CSV. If not, it will then check if there's a directory. So there's a directory, it will have to go into that directory, list the files, and character by character will go down the file structure. Yeah? Eventually, let's do that. So basically, that is the file structure. That's the path you take in this file structure. And then you end up with this CSV file. Yeah? It's this CSV file here, corresponding were these characters. These characters are also called a prefix. Yeah? So they're a part of the number. Yeah? Starting from the beginning, some of the numbers, those are called a prefix. And that is a pass. And when you look at that, we hopefully find that one. I think it's somehow... let's search it, right? Here it is. Yeah? So that is the entry. Yeah? So what is the price I paid for organizing data in such a structure? I mean, on the slides, it looked like, okay, I have these partitions, these horizontal partitions, and I rewrite the query to only look at such a partition. That's what I could do here. Huh? I basically identified this partition, and now I only have to search in this partition rather than search in the original file. But what is the price I pay for that? What's the difference to the original scenario where there was only the CSV file and I searched the CSV file versus to what I have now? Yeah, what is the effort I spent? Let's phrase it like that. Yeah, for being able to search down the paths in the file hierarchy and then only inspect this CSV file. What is the work I invested? Yeah. I did the search in the file hierarchy. Yeah, that costs something depending on how. Actually, I don't have to sort the data to make that happen. I'm not sure whether I sorted. I hope I did not sort, because you can basically tuple by tuple. Yeah? When you have a tuple in your hand, you just look at the first character, and then you write it to the appropriate CSV file. There's no need to sort it here. Yeah? And then you recurse. Yeah? Yes, you look at one tuple, and it's clear where the tuple has to be positioned. So basically, in the first partitioning step, you split the input file into at most 10 output files. That is what happens here. Yeah? Yeah, whenever there's a tuple starting with 6, you put it in the CSV file, 6 CSV. If it starts with a 3, you put it in the 3.csv file. That's one operation, basically the tuple being routed to the appropriate file. Yeah? No sorting required at that point in time. Actually, I think the data was sorted originally, and I shuffled it again to make clear that it works even when it's not sorted. I think it was something like that. But what is the effort I spent? And now I'm able to do this search. I can search that data because I created this structure on my file system. But what is the price I paid? Yeah, there's no free lunch. So what is the price I paid? It's still pretty big, that file, right? I had to read the entire file in the first place. I had to partition it recursively, write it multiple times on disk, back and forth for each recursion step. So I had to invest something here. Yeah? And other problems so that's the price you pay once, and then you can exploit it for multiple queries, of course. But then there are other trade-offs. For instance, what happens if elements get added to the original file? Well, then you also have to partition those files and append them to the appropriate CSV files. What if elements get removed from the original file? You have to remove them from your structure on disk as well, and so forth and so forth. Yeah? So you have to maintain that structure if the original file changes. So that's the price you pay. Yeah? But the lookup is in general much faster. You will learn later on in the algorithms class, algorithms and data structures, how you measure the performance gain of such a structure. Okay, yeah, the notebook is available in our CMS. I invite you to play with that a little bit. I think we can skip over that. Oh, we only have 10 minutes left, so how do we do that? Too many slides. Let me check what we... Yeah, I think we can start with that slide. So this is another visualization of an index, and it's called a binary search tree. And it's kind of similar to what you have seen before. So you could imagine this is your top-level directory, and each directory has two subfolders. Here's another folder, and here's another folder. That's how you could read it. Yeah? And then you run down the file system. In our example, we had in each directory at most 10 folders. This is limited in the sense, the structure, you have at most 2 subfolders in each directory. So if that's your top-level folder, you may only have 2 folders. That's one folder, and that's another folder. And recursively, so forth. There's only at most 2 folders at each level. That's called a binary search tree. And this kind of organization, however you represent it, be it a file system or some other structure in your program, can be exploited to query data. Yeah? So assume for a moment that you query 2. Yeah? You can basically start here, check whether 2 is smaller than 9. If that is the case, you run down this arrow. Yeah? If check it again, 2 is smaller 5, you run down this arrow. 2 is equal to, then this tree, in this case, has the convention that you run down the right arrow. Yeah? So for equality, you must fix once and for all, okay, what does it mean? Do I run left or do I run down the right arrow? That doesn't make a difference. You just have to set it once and for all for the entire structure. Yeah? So searching such a structure means at every comparison, you divide the search space by 2. It's half the space, half the data that you have has to be inspected. So you start by all data might be interesting. You do the first comparison, you're down to half of the data. You do the second, you're down to 1/4. You do the third, you're down to 1/8 of the data. It's only 8 elements, so you found the element. Yeah, so that's called binary search, and the structure is called a binary search tree. Now, in a map scenario with Google, you have problems like, okay, how do I search for a range of values? Yeah, all values from 2 to 14. And this range queries are not so easy in such a structure. So therefore, I mean, you could basically, if you want to have all values from 2 to 14, it's this entire part of the tree that's relevant. It's marked here with a shaded area. But it's not so easy to represent that. So, so basically what we want to have is something like that. This is called an ISIM structure, and it's very common in data processing. So basically, when you have a query like that, you translate it into a point query to 2. Here you run down the tree to this element, and then you have an extra reference here or pointer, however you implement it, allowing you to run along those entries here. So basically, the query starts like that, goes down to this element, and then it runs along those entries till it finds an entry that's strictly bigger than the 14 in this example, and then you found all of those elements. That's an ISIM, called an ISIM structure. Okay, let's explain it here on this slide. Not enough time here. I think we skip all of that. Okay, and why does it, maybe I think that's kind of important here. So why would that make sense at Google Maps? Well, you may have situations as follows, where assume again this situation where you're on a certain zoom level and you need to retrieve those tiles, yeah, maybe whatever, 4 tiles in X direction and 3 tiles in Y direction. So those are range queries. Yeah? That's basically written down here. So if, with respect to latitude, you want to have everything from 49 including to 50 including. That is a range query, a range condition. Yeah? This will retrieve 2 elements in that dimension times, and that is why there's an end. In longitude, there's another 2 elements, yeah, specified as a range condition. So on the database relation representing those tile entries, that is our relation cities, that is the range condition here on the latitude dimension and the range condition on the longitude dimension. So I'm using two different range queries to retrieve the corresponding entries for the tiles I'm interested in. So that's a relationship to what Google Maps is doing. Yeah? So when you zoom in, and we saw it here basically, yeah, so when I zoom in and zoom out, a certain number of tiles have to be retrieved. In X direction, there's a number of tiles. In Y direction, there's a number of tiles. And that entire square has to be retrieved. And that is basically where you have a range query, a range in the longitude and a range in the latitude dimension. So eventually, that has to be sent to a database to retrieve the right tiles. And those tiles can then be fetched from the appropriate file server. Yeah, that's the relationship to range queries. So there's so much stuff I wanted to show you, but can't in the interest of time. I don't know. I think bottom line for you is this horizontal partitioning stuff I showed you. Yeah, indexing you will learn about in detail in undergrad lectures and in the database systems course, of course, if you attend the core lecture. But the important thing is this trick with the, let's go back to, with the horizontal partitions. This slide is the important one. So organize your data in a way such that when queries come in and ask for certain data, you don't have to search through the entire data set, but you can somehow direct the search to an appropriate subpartition. The smaller, the better. There's a zillion tricks you can play to create those subpartitions, to put them in a tree structure like I did it here on the file system. It's a super long story, but just a high-level idea. In every scenario where you feel like searching through the data takes a long time, there's typically a variant of an index that allows you to decrease the search time dramatically. Yeah? So these indexes have a huge effect typically on search time. Okay, with that was a small outlook on databases. Next week, it's the intro to machine learning by Bernd Schiele. Thanks, see you then.